Welcome everybody to GeoHug. So before we do kick off today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal, of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, I am very excited that we have Isra Ezad joining us today. So Isra is a postdoctoral research fellow at Macquarie Uni and lectureship at UWA. She's an experimental igneous petrologist with an interest in the composition and melting behaviour of the mantle. Her recent work has focused on the role volatile elements play in the deep earth and how these volatiles can ultimately affect the mobility of base and precious metals during mantle melting. So Isra has applied these results to magmatic sulfide deposits with the aim to broaden our understanding of processes that lead to orogenesis from diverse mantle components. So this is going to be a brilliant session. I hope you all enjoy it. I'm just going to start promoting all up as panelists now, so please don't be shy. Come on through. We can kick off some great discussions at the end. But yes, thank you so much, Isra, for joining. It's amazing having you here.
No worries. Happy to be here. Thanks.
Brilliant. But yeah, before we do get stuck into your talk, I was really curious what got you into geology in the first place.
So I probably don't have a very interesting story, but as many millennials, I took a gap year and I went traveling. And I was really fortunate that I got to see some beautiful bits of the world. And I came back and I didn't want to do biology, but I knew I wanted to do sciences at uni, which is kind of ironic because I now work in a lab. And so when I got back, someone said to me, "Oh, have you heard of geosciences with a year abroad?" And I thought, I can travel and I can go to university. So
The
that's
perfect
actually
thing.
how I ended up studying geology.
That is awesome. And so what have been some of your favorite places that you got to see?
I really had an incredible time in China looking at the Dabi Sulu mountain ranges. They're stunning, eclogites, huge garnets. That was a real highlight during my PhD, being fortunate enough to go there.
That's amazing. And yeah, so you've recently done the transition as well to UWA. So that's really exciting. So what's your role there now?
Yeah, that's true. It's actually my first week here at UWA, so I've just accepted a lectureship position here. So yeah, I thought it'd be a good time to let people know what I'm doing and share some of the research that's happening in Australia.
No, that's brilliant. And I cannot wait to hear it. So thank you so much again for joining us. If you want to share your screen, and yeah, I'm excited to hear it all. So thank you.
Before I get started, I'd just like to acknowledge all of my wonderful collaborators and colleagues who are listed down the bottom there. Science is rarely done in isolation, and these people have been really important for me being able to bounce ideas off them. They've been really great at sitting and listening to me when I've come back with an experiment and gone, "Oh, I don't know what this means." And so a lot of this work is really a collaborative project over a number of years. So I'd just like to acknowledge them before I get started. So we're going to go back to basics for just 2 minutes, and we're going to reassess really how we've determined the composition of the mantle. How have we got to our beautiful green interior? And I love peridotite. It's one of my favorite rocks. It's beautiful. It has garnet sometimes, but really, how have we ended up being sure that that is the composition of our planet? Well, we have a whole host of natural samples. Mantles endless, they come up in a variety of volcanic eruptions and all over our continents, and indeed in the oceans too. So they've been really prime in helping us to understand what the composition is from a geochemical aspect. We've been able to combine this with geophysics, particularly looking at seismic velocities and changes with density within the planet. And if we combine these with experiments, which is really the work that I do, we've ended up at our lovely green interior. And so what does that mean when we're thinking about some of our base and precious metals? So for this talk, I'm really only going to focus on nickel, but this could be applied to a number of different metals. And so we've been able to not only measure where certain elements are, but also look at their partitioning behavior, which really controls where these metals will be and in which phases within our mantle mineralogy. And so when we look at nickel, for example, it will come as no surprise to many people that it is predominantly partitioned within olivine. Olivine is the major host for nickel within our planet. And the reason for that is because of the structural controls and those partition coefficients. So when we're thinking about why we might want to revisit nickel systems, if I'm telling you that we already know where the nickel is and in what mineral it is, it's because we need to try and understand actually how we liberate nickel from peridotite. And so the way that we can relook at that system is by revisiting some of that really important work that Noldra did and trying to understand the way in which the mantle melts. And so mantle melting typically begins at about 1325 degrees at roughly 90 kilometers depth in the mantle. And what you will see here is this purple line that's showing you the nickel concentration in the melt that is liberated when peridotite starts to melt. And that line is pretty flat. It's more or less around 400 ppm. So that means whilst we liberate some nickel from the mantle, it's really not that significant. And to show you why that's really important, is that we actually have an incongruent melting reaction. So what that means is that when we have melting beginning, we're not melting olivine, but worse, we're actually crystallizing olivine as a product of that melting reaction. And so that means if nickel is interested in being within olivine, any of that nickel you're liberating, some of that will end up back in the residue. And that's exactly what that red line is showing you in the top right. And then you can see there that the nickel concentration is actually increasing from an initial of about 2,500 ppm to something like 3,500 ppm after just 25% of partial melting. There are, of course, always exceptions. And so the exception here is komatiites. And so during a young, hot Earth, we were able to actually generate significant temperatures, which allowed us to actually melt olivine. To try and understand why that's important for modern day settings is that if we really look at how we generate magmas from peridotite, we have three key geodynamic locations. We have mid-ocean ridges, hotspots, and arcs. And so we've got a really good thermal understanding of what the temperatures are in those three locations. And if we just look at that compared to the percent of melting for a peridotite setting, we go from very low degrees of partial melting. We can produce something like a nephelinite or perhaps a basanite, where I'm about 10% of partial melting. Anything greater for our mid-ocean ridges and even our hotspots, we might get to a tholite or a picrite, which is about 25% partial melting. To hit a komatiite, you need to melt about 40% of that mantle source. And you need to do these at extreme temperatures. And those temperatures we just don't have anymore. So that means if we're trying to understand the behaviour and where we might start looking for nickel deposits in a slightly older Earth, then we need to try and look at settings where we can actually melt things which are rich in nickel, which are not peridotite. To really drive this home, peridotite produces a really restricted composition of what we call primitive melts. Primitive melts are those that we expect to be in equilibrium with our mantle sources. And so if we go back to a TAS diagram, what we'll see here is those purple triangles. They're really showing you the chemical extent of melts which are actually in equilibrium with their mantle source or a peridotite mantle source. All of those blue dots that you can see, that's essentially just noise. That's either due to fractionation or some other process. So those melts aren't representative of things which have come from a mantle source. And so that becomes really challenging when we're actually looking at our search space because we are geochemically limited. We're limited by the geodynamic setting, and we're also not melting olivine anymore. So that becomes a real challenge. So where else can we look? We can have a look at alternative mantle sources and what I like to call the other primitive melts. The Tanzanian Craton area is a really good location for us to start to look at other primitive melts. So those melts that are still in equilibrium with a mantle source, but they're not in equilibrium necessarily with a peridotite or an olivine-dominated mantle source. And so we can have things like kimberlites, chamafugites, which are really potassium-rich melts, nephelinites, which are more sodic-rich, basanites and alkali basalts, and carbonatites. And so what you have there is that as you go from the top of the list to the bottom of the list, you have increasing volatile additions, so things like water and CO2, but you also have increasing alkalis. And so this diagram here on the left is really showing you the extent of where peridotite melts can produce these really alkaline-rich melts. And they're barely touching those potassic systems, those alkaline systems. And quite often we see alkaline systems associated with our magmatic sulfide deposits. And so we need something else. So what else is there? Well, I'd like to introduce you to the dark side of the mantle. And these are hydrous pyroxenites. So this is a beautiful example from Uganda. It's an amphibole mica pyroxenite. This is a component of our mantle. And it's mostly been ignored, one, because it's so dark. So when you pick these things up in mafic magmas, it's really easy to miss them. But we've had some incredible work that has come out from South Africa. Really, they've driven our understanding on this dark side of the mantle. And they've been able to term two specific groups. We have the marids, which include mica, amphibole, a whole heap of accessory oxides like rutile and ilmenite, and diopside. And then we also have our picks, which are phlogopite dominant, ilmenite, and clinopyroxene. And just like those peridotite xenoliths that we get all over continents and in oceans, we also have these hydrous pyroxenites coming up as mantle xenoliths. They're not scarce components in the mantle. They are extremely interesting and they have such a wide variety. They can range from something that looks like on the right-hand side, about a third each of a hydrous mineral like phlogopite, clinopyroxene, and titanomagnetite, to something on the left-hand side, which is almost completely composed of phlogopite there in the red. And so that means that we have a whole range of different minerals present in this mantle component. What's really important to note, though, is that these hydrous pyroxenites are olivine-free. So there is no olivine within these metasomatic hydrous pyroxenite phases. And so we've been doing a whole load of melting experiments to try and understand the behavior of these things. We really understand how peridotites melt. We know what the melting reaction is, and we know essentially where the metals are moving during partial melting. That's not true yet for hydrous pyroxenites. We're really starting to get a handle not only on their mineralogy, but their melting behavior. But importantly, where is the nickel? So here we've been able to compile together again those partition coefficients, which are a measure of which mineral nickel is going to likely be in. And so those top four minerals there, therefore, are peridotite settings: olivine, orthopyroxene, clinopyroxene, and garnet. Everything else, these are minerals that are common within hydrous pyroxenites. And I'll just draw your attention to these three here in the middle: phlogopite, potassium richterite or potassic amphibole, and sodic clinopyroxene. These particular minerals have extremely high partition coefficients, in some cases greater than olivine. So what that means is that if we have melts percolating through the mantle and passing these phases, or indeed crystallizing these phases, any nickel present in those melts will be sequestered into these hydrous phases. So that's quite incredible. We have a different store for nickel within the mantle. And it's not just nickel. I'm not going to spend too long on this slide, but I'll draw your attention to those first row transition elements in the middle there: copper, zinc, cobalt, scandium, and nickel. These are all elements that are extremely compatible within a whole host of different minerals which form our hydrous pyroxenites. In particular, amphibole, phlogopite, and ilmenite, because they have a crystal structure which is really accommodating for some of these transition row elements, they actually become excellent sinks for these things. So we need to be exploring a bit wider when we're looking at what the mantle sources are for some of our deposits. So as I said, we've been doing a whole host of experiments to try and understand the melting behavior of these hydrous pyroxenites so that we can really start to pinpoint geochemically and geophysically where these things are occurring. And the most important thing is that the melting temperature for all of these different hydrous pyroxenites is significantly lower than dry peridotite, or indeed wet peridotite. So dry peridotite here is in the green line, and you can see that the melting temperature is just shy of 1300 degrees. If we add water to our peridotite settings, which we often do through metasomatism or subduction, then that does reduce the melting temperature of a peridotite lithology. But for all of the hydrous pyroxenites, their melting temperatures are again below that. They're closer to about 1000 or 1050 degrees. And so that means that you don't necessarily need a huge thermal anomaly to melt these components in the mantle. We're no longer looking for large igneous provinces or with plume-induced melting. We actually just need a small tectonic nudge, some thermal relaxation, and then you can trigger melting of these components. And that also means that they become separated away from that peridotite component, which remains solid. We don't often get a chance to showcase actually what experiments look like. So I thought I'd put this in here for everyone who's not familiar with experimental petrology. So the image here on the left, that is a rapid quenching piston cylinder apparatus. And what you can see there is essentially a very, very small hydraulic press. And we're able to recreate conditions at lithospheric pressures and also within the mantle. And so you can put in a capsule which is no bigger than about 2 centimeters into the middle there, and then you get compression from the top and the bottom, and it is hydrostatic, and then you can heat it up. And then the output of those experiments is essentially a tiny, tiny thin section. So if you're used to looking at thin sections, then you can be an experimental petrologist because you can recognize the same minerals and phases and textures that you would see in natural rocks as you would in experiments. And that's why they're really powerful for trying to understand processes. So that picture on the left there is just showing you one of those experimental products. And I'm sure many people instantly recognize those phlogopite leths. We've got clinopyroxene and we've got melts. So they're really good for us to be able to, in a cleaner environment, you can pinpoint the process you want to test and you can do those with experiments. So I think it's a pretty powerful tool for us to try and understand some geological processes. So melting of hydrous peroxides. This is the kicker. So if we take, for example, a rock which has a third of potassic amphibole, a third of clinopyroxene, and a third of phlogopite, and we start to increase the temperature along the bottom there, we start to generate melts very quickly, and we actually start to consume all of our potassic amphibole within about 50 degrees of crossing the melting temperature. The problem here is, similar to peridotite settings, this is an incongruent melting reaction. And you'll see there, we've gone from an olivine-free rock to a residue which actually has olivine. So that becomes a problem if we're trying to liberate things like nickel from these hydrous peroxenite assemblages, because the growth of that olivine is going to probably try and sequester some of the nickel present in that melt into olivine. But the composition isn't that simple. And so we've actually begun doing experiments where we've added accessory minerals, which we know are present within the natural rocks, things like ilmenite, rutile, or apatite. The addition of accessory phases actually reduces the volume of olivine that's grown during incongruent melting reactions. But importantly, in the case of the addition of apatite, it completely kills off olivine. So you no longer have an incongruent melting reaction, and now you're generating melts in the absence of olivine growth, which means all of the nickel that's liberated during partial melting will remain in that melt, meaning that it's now available to be moved up into the lower crust. So that's really key for us trying to look at and understanding what these melting reactions are. So do we have evidence for hydrous peroxenites? It's one thing to say that I've got this rock and we can do the melting reactions, but in fact, we have evidence that they are widespread and in a number of geodynamic settings. So cratonic assemblages, for example, they tend to be really enriched in things like potassic amphiboles, potassium richterite. And like the experiments that I just showed you, amphibole tends to melt extremely quickly and completely. Phlogopite tends to melt more gradually. And so we actually end up with compositions which are lamporitic. These are potassium, volatile, fluorine-rich melts, and they occur on a number of cratonic regions, and they're often co-associated with things like our nickel or VMS deposits. You can see a global image down the bottom there. Non-cratonic regions, they tend to be dominated more with calcic amphiboles, and we see their influence really in arc settings. So in the case of calcic amphiboles, they're again melting very quickly, and these will produce things like nephronites or basonites, things that we commonly see associated with arc settings. And what about intraplate volcanism? Here's an example from close to home. Eastern Australia has one of the longest intraplate volcanism tracks anywhere in the world. And this alkaline volcanism is extremely rich in both potassium and sodium. And here we think phlogopite plays a really key role in generating some of those compositions. So we have plenty of examples where hydrous peroxenites are a requirement in the mantle source to produce some of those primitive melts. So how do we produce nickel-rich melts from the mantle if we consider a source of peridotite and a source of a hydrous peroxenite? So again, here we've been able to recalculate those melting reactions, this time using thermodynamic modeling, just in case you don't believe the experiments. And now here you can see that on the bottom is the melting behavior of peridotite. And again, we modeled pretty much what Noldra had. We had, in fact, 400 ppm of nickel present within those melts, and it doesn't really change until you get way up past about 30% of partial melting, which we know just isn't possible in today's Earth. What about hydrous pyroxenites? Well, at the offset, we have about 600 ppm of nickel present, and that starts to increase quite gradually as we have amphibole leaving the system at about 15% of partial melting, and then it starts to skyrocket. And that's because any of that nickel that was held within amphibole will then be released into those resultant melts. I'll just point out that when we did the thermodynamic modeling, we actually used the reaction which had the growth of incongruent olivine, just to make it a fair test for both these cases. So the reason that hydrous peroxides, I think, are a really important and probable source is not only do they produce nickel-rich melts, but actually they melt in large volumes. They have quite large degrees of partial melting, which is in contrast to the way that peridotite melts. And really the way to look at this is if we have a look at this second diagram, where we've got temperature on the y-axis, by the time we've hit about just 100-degree increase in temperature, we've gone from 0% partial melting to all the way up to 30% partial melting in a hydrous peroxide. To get an equivalent amount of partial melting in a peridotite system, you actually need to shift the temperature by more than 200 degrees. And these are extremely elevated temperatures already. We're talking about temperatures above 1350 degrees. So that means that even before peridotite starts melting at about 1300 degrees, if you have hydrous peroxide in the region, you will have melted that to about 60%. And so that means you're producing these really supercharged melts at the expense of where you might have had very small degrees of partial melting of a peridotite. So let's just have a look at the global distribution of nickel, copper, and PGE magmatic sulfide deposits. It'll come as no surprise that the majority of these are actually associated with cratonic margins. And a lot of this we know already, and we've already been searching cratonic margin regions. And our understanding has really been that we need this big plume driver. We need a huge thermal anomaly to cause this large degree of partial melting. And then this is kind of those regions that we've been looking at. But if we have a look at the global occurrence of these primitive alkaline melts, they also co-occur on cratonic margins, things like lamperites, ultramafic lamprifiers, and kimberlites. But we know that we cannot produce these alkaline, volatile-rich melts from a mantle plume setting. And a lot of these primitive melts occur at a similar period in Earth history to where we have those deposits. So likely they were tapping a very similar mantle source. And so it goes back to when we're trying to understand what the cratonic architecture is in those settings. And we've got really excellent geophysical surveys which look at what the cratonic architecture is. And we don't have this clean bowl shape that we often draw in a lot of our schematic diagrams. What we actually have is something that's been nibbled and gnawed. It's got all of these indents within that cratonic base. And so these become regions really where we can start to change the composition of that cratonic keel. And that means we can actually introduce some of these small metasomatic melts. We can change the composition of the cratonic lithosphere. And then we can actually, when we generate our melts, they're something different. They don't need this big plume impingement in order to initiate melting. So the way that I like to view this is that instead of having this lovely smooth bowl, perhaps we have a series of more complex and smaller scale reactions that are occurring over time. So in step one, we have this metasomatism of our cratonic root by incipient melts. Then we have to have a reaction of these melts within the cratonic lithosphere, and this will generate our hydrous peroxides. We know that these tend to occur as dikes and veins, and they also infill cracks. And we've got beautiful examples where we have veins of hydrous peroxides in those mantle xenoliths. Over time, these dikes and veins, they will grow, they will channelize themselves from peridotite, essentially making a highway, so that when melting is initiated, they're not significantly reacting with surrounding peridotite and causing contamination, but actually what you're having is a really direct pathway to the lower crust where we can have those upgrading mechanisms occurring. And so here's a beautiful example of this in action. This is a mantle xenolith from Patagonia. And here you can really clearly see this gorgeous phlogopite vein cross-cutting this peridotite. And here, this is the introduction of those incipient melts, or those low-degree metasomatic agents, which are changing the composition of the surrounding peridotite. And then when you start to look closer, you see things like amphibole, you see carbonates, and you see sulfides. More recently, we're starting to accept that there's a really important role for carbonates or carbonatites in the mobility of things like sulfur and also some of our base and precious metals. And so we've also been doing experiments to try and understand what this relationship is. It's not enough to know what the melting behavior of those hydrous peroxenites, but we also want to try and understand how these things are forming and can we use some geochemical constraints to track them. And so we've been experimentally producing these low degree or these metasomatic melts in both peridotite lithologies and pyroxenites. And here, what I'm showing you is actually these carbonatite melts. So whenever you add volatiles, either water or CO2, into either a peridotite or a pyroxenite lithology, you actually end up producing a carbonatite as those very small, very volatile, extremely reactive melts. And this is what they look like when they're frozen. They don't look like your typical melt or glass. They fall apart into tiny, tiny little minerals, usually carbonate minerals, hydrous phases, and they are a nightmare to work with, but beautiful to look at. So we see them along melt interface grain boundaries. And what we also find is that these small degree melts, these incipient melts, they're able to actually mobilize sulfides. So the example here on the left is a really nice example where we have a melt interface. On the top left corner, we can see the original peridotite olivine. And on the bottom left there, you can see the metasomatized clinohumite. Clinohumite is essentially a hydrated olivine. And on that interface, we actually have sulfides, which have been mobilized by these carbonate melts. So we've been having to look at these again, and we've been basically seeing below the surface. We've been doing transmission electron microscopy on those two sulfides that you saw in the previous image. And what this really means is it's similar to if you were excavating on site and you were trying to get a cross-sectional view of what's happening, or you're at a road cutting. That's exactly the process that we've done in our experiments. And so what we were seeing previously from the surface above, we've essentially just cut through, and now we're looking at this as if we were looking at a cross-section of the road. And what you'll find here is that we have two beautiful sulfide blebs. They're associated with carbonate melts, and they also have these really high density cores. I'm hoping that you'll be able to see these. These high density cores, we've then been able to go in and have a look at again in more detail. And what we found is that these sulfides have actually acquired platinum group elements, PGEs, platinum and iridium, from that surrounding network. The sulfides are actually now both iron and nickel rich. During our experiments, we only added sulfur present as iron sulfide. These were really barren sulfides initially. So somehow, during the process of that incipient melting, these carbonate melts have been in a really effective vector, a metasomatic agent, sequestering all of these metals that we're interested in and getting them to those sulfides. It's not just platinum group elements, but when we actually start to compare either side of that boundary where we had that quenched sulfide and that metasomatic melt, we've been able to go back in and actually look at the trace elements between our clinohumite and our original peridotite olivine. And so what we'll see here down the bottom is that going from the orange to the blue dots is essentially looking at the transport of some of those metals that we're interested in. And in the case of the peridotite olivine, of course, it starts rich in iron, nickel, copper, and cobalt. By the time the melt has interacted significantly with that olivine and produced clinohumite and also the sulfides, we see huge decreases in things like iron with a compensation of an increase in magnesium. We've basically stripped out all of the nickel from olivine without melting it. That's really important. And we've also stripped out basically all of the cobalt as well. And so the way that I envisage this reaction happening, I have a very basic cartoon to show you all. So we have olivine. So let's imagine for a moment that our olivine is full of those metals, iron, copper, cobalt, and nickel. We have the percolation of our carbonate melts. Carbonate melts are really important, and they're really, really effective reagents because they interconnect at extremely low volumes. You need just 0.03% of carbonate melt and they interconnect. And the reason for that is that they're actually less viscous than water. And so whenever they find the opportunity, they will interconnect and they will start to react. They then actually react through a mechanism called precipitation and co-precipitation. So they start to react with those grain boundaries. And the chemical drivers mean that they actually carry things like sulfur. You'll have to believe me that they carry sulfur or read the paper, because I probably don't have time to talk about it just yet, but we can in the discussion. And so this chemical potential gradient and the dissolution and co-precipitation mechanism means that you transfer a lot of these base metals into the carbonate melts. In exchange, you end up hydrating your olivine, and that turns to clinocumite. That's the reaction product. And eventually, all of those metals end up in the sulfides. And that's exactly what we see not only in Mantle's endless, but also in the experiments. And so to go back to this image here, hopefully I've convinced you that we can cause metasomatism in the cratonic route. We only need these metasomatic agents, which we're getting much better at pinpointing what they are, how they mobilize metals, and how they interact with the cratonic lithosphere. That then means that over time, we're able to really enrich these cratonic sponges or roots, and they kind of suck up a lot of these components that are present within the mantle. They become enriched in things like base and precious metals, and then over time, they can remelt. So I have one example, which I think is a really nice example of perhaps where we do have a metasomatic origin, or where hydrous peroxenites have played an important role, and that's Voisey's Bay. So Voisey's Bay is on the edge of the North Atlantic craton, so that's already a tick there for the cratonic region. And predating Voisey's Bay, we actually have alkaline volcanism. So just down the road in Isla Bay, we have 1.37 billion year old lamporites. So those lamporites, they're those potassic, volatile, rich magmas. And then we have Voisey's Bay, which pops up at 1.34. Subsequent to Voisey's Bay, we then have over 600 million years of volcanism, which is again alkaline, carbonate rich. So the mantle here is really enriched in some of these components. It's very volatile rich. It's rich in potassic systems, and it's also tapping deep sources as well. So I think Voisey's Bay is a really nice example, perhaps, where we do have a clear evidence for this metasomatic origin. So I'll just leave you with some future directions. I think I'm okay for time. Yeah. So I think this is perhaps some ideas or some kind of future areas of research that we should be concentrating on to try and really focus in on what the mantle component is, and how, if we're not just thinking about a green mantle, but the dark components, how can we use those to inform some of our decision making and science? So cratonic margins, they have these over-thickened metasomatized roots, or sponges essentially. And we know that these incipient or these metasomatic melts will be active at extremely low geotherms. So perhaps we need to use geophysical imaging to help us try and trace some of these metasomatized regions of the mantle. We know they have a different geophysical response. So hydrous peroxenites typically melt to higher degrees of partial melting than peridotite, and they form potassic primitive melts typically. And these are rich in chalcophyll elements. They also tend to be extremely enriched in their trace elements as well, and rare earths. We know that a lot of these melts occur to known deposits, especially in the African nickel belt. We've got really good understanding there. Proto-rifts are a really good place that we should be looking, particularly going back in Earth history, because they tend to erupt geochemically unusual primitive melts. And even these failed rifts, they tend to re-bring up some of these components in the mantle. So I think that's a really good area where you actually telescope some of these precious metals. This is kind of a call out to the community. I think we should be measuring our chalcophyll, base, and precious metals, particularly in those hydrous minerals or accessory minerals, particularly things like mica, apatite, and amphibole. We've really kind of ignored these hydrous phases as potential sinks for some of these metals, but we're actually starting to get a bit better at that. So I think we need to continue that. We need experiments to understand sulfur capacity of carbonate systems. Of course, I've not really touched on sulfur during this talk, but sulfur is, of course, the driver that we need for our magmatic sulfide systems. So we need to understand really well how we're actually mobilizing sulfur within the mantle and what that link is to the lower crust. That's really important to target next. It's interesting, carbonate lavas, they are geologically young. They tend to pop up from the Paleoproterozoic. So what changed? Did we go from a reduced to an oxidized mantle? Something changed in the planet. And I will leave that there.
Thank you so much. You are a brilliant presenter. So thank you. That was awesome to learn about and see everything you've been doing. So thank you so, so much.